This Unreal Engine 5.5 drone follows a closed three-dimensional path built with USplineComponent. The path contains 6 control points, rises and falls in Z, and is visualized by 56 real marker instances. The drone moves at 520 Unreal units per second, rotates with the path tangent, reports its traveled distance, crosses 25, 50, and 75% milestones, and completes one verified loop. In this lesson, we will build the spline, treat distance as the movement state, advance that distance with speed times delta seconds, sample a world transform from the spline, choose loop or clamp behavior, and verify the result with native runtime frames, structured logs, and an Unreal automation test. The route lives in a spline component attached to the actor root. This demo clears the default points, adds 6 local space positions, enables a closed loop, and updates the spline once. Unreal then builds a smooth curve through those points. Keep the path separate from the moving mesh. The spline answers spatial questions, while the drone body is only the object being positioned. This makes the same movement code reusable for cameras, platforms, patrol units, projectiles, rails, and cinematic props. In production, designers can edit the points in the level instead of hard-coding them. The movement state is one float, distance along spline. It starts at 0 and advances in Unreal units. The spline reports a total length of 3,751.5 units, so normalized progress is simply distance divided by length. Distance is usually easier to reason about than a raw 0 to 1 alpha because speed also uses world units per second. A speed of 520 means the actor covers the same path distance each second, independent of frame rate. The curve may bend or change elevation, but the distance model remains stable and testable. Each tick calculates travel as non-negative speed multiplied by non-negative delta seconds. It adds that travel to the current distance. A looping path uses floating point modulo to wrap back into the valid distance range. A non-looping path clamps at the spline length. This logic is isolated in the static advanced distance function, so the automation test can verify ordinary motion, wrapping, clamping, negative delta protection, and a zero-length spline without creating a world. Keep time math pure when possible. It is one of the easiest ways to make movement behavior deterministic and regression-friendly. After updating distance, the actor asks GetTransformAtDistanceAlongSpline for a world space transform. The return location places the drone on the curve. The returned rotation follows the spline tangent, so the body naturally turns as the route bends. The transform can also carry scale when that is useful. Do not separately invent position and facing direction if the spline already owns both. Sampling a single transform prevents visual disagreement between where the object is and where it points. You can still add an offset, banking, smoothing, or look-ahead rotation after the base path transform is correct. A spline does not automatically appear in a package game, so this demo samples 56 distances around the loop and places instance sphere meshes at those transforms. Every 7th marker is larger. This is visualization code, not the movement source of truth. Using an instance static mesh component keeps the marker draw cost lower than spawning 56 separate actors. More importantly for debugging, the visible dots come from the same GetTransformAtDistanceAlongSpline query as the drone. If the markers and drone disagree, the bug is in how transforms are applied, not in a separate hand-drawn illustration. These are genuine game mode frames rendered by Unreal. Near 8%, the drone is on the right side of the loop. Near 48%, it has crossed to the upper left curve. Near 86%, it is on the lower right return path. The body orientation changes with the tangent, and the world space progress label changes with traveled distance. The scene is captured through Unreal Scene Capture Component 2D and a texture render target. No generated game image is substituted for runtime evidence. The same executable run also records each milestone and the completed loop. The Unreal Automation test passed with 1 success and 0 failures. It verifies speed times delta, looping from 950 to 50 on a 1000 unit path, non-looping clamp at 1000, negative delta protection, zero length handling, and normalized progress. The runtime then proves the parts a pure test cannot. Spline length 3751.5, speed 520, 56 visible markers, milestones at 25, 50, and 75%, 3 native captures, 1 completed loop and valid true. Use both layers. Math tests catch edge cases quickly. Runtime evidence catches integration and rendering mistakes. The reusable pattern has 4 steps. Build or reference a spline path. Advance a distance with speed and delta seconds. Sample a transform at that distance. Apply the transform to the moving object. Then decide explicitly whether the end should loop, clamp, reverse, stop, or trigger an event. For moving platforms, prefer controlled collision movement when passengers must be carried. For network games, replicate authoritative state rather than trusting independent client ticks. For cinematic motion, Sequencer may be a better authoring tool. But for compact C++ path following, DistanceAlongSpline component is a clean, AI-friendly, and highly testable foundation.